Talk about 3-1. Set the foundation for a lot of the stuff that we're going to talk about in the coming weeks. This becomes one of the most useful tools for the rest of the course. Some common vocabulary that's going to kind of have later implications, and in regards to if I can understand it now, then when I see 3, 4, 5 other types of vocabularies later on, or definitions later on, I should be able to maybe understand those as well, because of how you interpret the ones we see here. But 3-1 is lines and angles. Kind of talk about parallel first, okay? So it's kind of, there's really two ideas going to be happening in today's lesson. We're going to talk about parallel lines and skew lines, and how we recognize those and how we reference those. And then we're just going to talk about a completely different concept, and basically being able to identify and name certain types of angles. And it's just basically vocab. But the reason is tomorrow we're going to mesh those things together. Parallel lines, skew lines, and then what we learn with the naming of certain types of angles. And see what relationships we get from doing that. Okay. But the first thing today is parallel lines. They are coplanar lines that do not intersect. From what you guys know in, say, 7th grade, 8th grade, whatever grade it was that you first talked about parallel lines, you probably left that word out. Okay, they probably did not talk about that. Okay, because the assumption at that stage was, one, maybe we don't have enough math under our belt to really understand what coplanar meant. Or two, we're never going to deal with things that are non-coplanar. So let's just eliminate that word out of there and just talk about two lines on the same plane. Okay, and that's really what coplanar means. They have to be in the same plane. If we think about just kind of give you a visual here, if you take two lines, no matter how they relate to one another, whether they intersect, okay, or they are parallel, those are your two options right now. But is there, visualize a piece of cardboard. Could I put a piece of cardboard and rest it completely on both those? And that cardboard will touch the entire set of lines. Not just a point on each line, but it'll touch this entire line and it'll touch that entire line, right? Okay. Even if they intersect, is there another piece of cardboard they could lay on top of those that piece of cardboard will touch both lines? Okay. Now, what we mean by that, when I say touch it, I really mean contain. Okay, to where this line here is inside that whole piece of cardboard, and same thing for that. Okay, and no matter where you put them in three-dimensional space, as long as they're intersecting, they're going to be coplanar. Does that make sense? Okay, no matter if I lay them like that, you could put a piece of cardboard on top of that, and those two lines are going to be in that cardboard. Okay, parallel, they don't touch. So, but we can still have that idea, that concept. I can take a piece of cardboard and lay it on top of those, and that piece of cardboard is always going to contain both lines. Okay, even if they're parallel like this, maybe they're parallel like that, maybe they're parallel like this. Okay, there's still a plane that could touch both those lines, right? So that's what parallel means, and that's why we mean coplanar, is that there is one plane that can touch both lines. There is not one plane that can touch those two lines. Okay, and those two lines are skew. And I'll show you some pictures here on the board of skew lines as well. Okay, but the key thing for us right now is that it's no different than the definition that we've learned and the way we view it and talk about it in 7th grade, 8th grade, 9th grade math. But now we're going to incorporate that word coplanar. Okay, because when we take it out or when they negate it, it provides something else, something new. Okay, that symbol right there. Just means parallel. You've probably seen that before. What is nice in regards to parallelism is that it's symmetric. And what I mean by that, if I look at that phrase right there, AE, that line is parallel to BF. Okay, so AE, that line, parallel to that line BF. It's symmetric in the event that I can say BF is also parallel to AE. You can read it both ways, right? You can flip it around. And still be okay. Still get the same result. And that's something we like to do in all types of mathematics, is deal with, does this relationship have symmetry? Can you look at it from both aspects AE compared to BF, and then BF compared to AE, and still arrive at the same results. In parallelism, you can do that. Okay? So that's the way we want to talk about it, but let's talk about some ways that maybe you've talked about it in the past. If we have... Oh, I didn't want that one. I want... Let's make a new one. If I have that line there, and what GeoGebra does is it creates a tool that will force things to be parallel. Okay, so I can take those two lines. Notice over here, and I'm actually going to change this into y equals mx plus b form. Okay, what did you learn last year about two lines that were parallel? What is that value there? What is that negative 0.32? What does that refer to from last year? Slope. Okay, so what do you see in between those two slopes? They're what? They're equal, they're the same. And that was the relationship that you talked about last year, is that whenever two lines have the same slope, they are parallel. It's going to be a huge principle that we use in this course and quite a bit. You remember using the distance formula, the midpoint formula, and the algebra that we had to do with that stuff? When it was in the XY plane. We're going to use slope quite a bit in conjunction with those two formulas in the next couple weeks. Okay. So if you can't remember slope, we'll talk about it a couple times, but it's your change in your y direction divided by the change in your x direction. Okay. But the rate in which these two change is the same. Okay. So the rate in which that slope changes and the rate in which this line slope changes is the same. Therefore, they will never meet. Right. Okay. That's kind of what we talked about last year in Algebra 1. Another way of talking about parallel lines comes from this idea, and really I'm going to kind of help us build to this idea before we really talk about it in depth. If I were to give you that point there, and I give you that line right there, okay, so let's say we got this point, see what its name is, point A, and let's see what this line is going to be called, line F, okay? Let's say that, this is maybe the classroom. So let's say that's our classroom. This is the wall behind you guys. And this is maybe where I'm standing right now. Does that kind of make sense? Okay. Now I'm going to get rid of that square, but kind of visualize it that way. And you're looking down in a bird's eye view of this. Okay. And I ask you, how many different ways can you walk from A to that wall or to that line at the bottom? How many different ways could you do that? You could do it in an infinite number of ways. Okay. So I could say, and I'm going to get that name up, so that's point D. Would you agree that that segment, that red segment, would be a path from where I'm at to the wall behind you, right? But that could change, right? That could be one pathway, and maybe that gets me to my bookshelf, okay? And maybe this path gets me to the door, right? Maybe this path gets me to my podium, right? Those are all different pathways to get from A to that wall, all right? But when we ask about the distance from A to that wall, okay, each one of those paths has a separate distance, right? So I'm going to ask GeoGebra to find that distance for me. So that distance right now is 7.06, okay? So maybe from where I'm at to the door would be 7.06 meters or something, or feet, whatever, okay? But as I move and create a new path, that distance changes, correct? Okay? Now, hopefully you realize that if there's an infinite number of paths, there's an infinite number of distances, right? Okay? Now, kind of visualize this. Let me zoom out real far. Okay? Can you kind of visualize that distance? Okay, if we imagine that wall or that line going on forever, that distance doesn't have what we call kind of an upper bound, right? That 35.1 could continue to grow to infinity. Does that make sense? Okay, but it should have a lower bound. There should be a distance that I can walk from that point A to this wall that is, come on, that is the shortest. Okay? So I should be able to, you see that number's decreasing, right? Decreasing, 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 and now it starts to increase again, correct? Okay? So somewhere in here there was a shortest distance. So when I ask you, what is the distance from where I'm at right now, or from the distance of A to this wall, I just say, what is the distance? It's an understood phrase that should maybe more explicitly say, what is the shortest distance from A to the wall? Does that kind of make sense? Or from A to the line? And that shortest distance is always found using a particular type of angle. If I find that shortest distance, actually let me get the grid here. Okay, right there, and that's not right, there you go. 5.01. There we go. What do you notice that shortest distance, that's 5. So we go 5.1, 5.05, get to 5, and then after, there's a little bit of rounding going on, but after I get to 5, that angle starts changing, right? But when it was the shortest distance, that angle measurement was 90. So when I want to measure distance from a point to a line, I always do that with perpendicular lines, right? Okay. Hopefully maybe you understand the logic of why we would do that. If I wanted to retile this room or put a different floor down in this room, I would want to first find the dimensions of it, right? So I'd come to this corner over here and I'd put a tape measure right here in this on the floor on this wall, right? Somebody else would take a tape measure and go down there, correct? Where at on that wall would they go if I wanted to find the dimensions of this room? Opposite. Careful. If I want to find the length and width of this room so we can find its area, why don't we go straight there? Okay. We're gonna go perpendicular from where I'm at right now to that opposite wall. All right, and we're going to use right angles to do that. Okay. Can I find the length of this room if I started from here and went that way? Yeah. But what would I have to do? I had to make sure my tape measure, when the person is on the other side of the room, we would have to make sure that when they put the tape measure down on the ground, they're creating a right angle with the tape measure and that wall. Does that make sense? Or we will actually use a distance that is longer than what we want. If I use a distance that's longer than I want to find area, that means my area is going to be greater than what I want. And then when I go back buy the materials, I'm going to buy more material than I want. I'll waste money. Does that kind of make sense? Okay. So when we want to find distance between a point and a line, it's the shortest distance possible. And we use perpendicular lines to do that. Now, the reason we talk about that is because I want to talk about how another way we can talk about what parallel means. Okay. Those two lines, I've used GeoGebra to say that those two lines are always going to be parallel. I can move them around, change them, but however I change them, they're going to be parallel to one another. Okay, and I can grab them and change the distance between them or whatever. But right now, I've got a point E, okay, and I want to know from E, what is the distance from E to the red line? You notice I used a right angle there, right? So I'm finding that shortest distance. And it's saying it's 11.69 units long. Okay? Well, when I move E, it is now a different point on that blue line, right? So maybe maybe the idea here is that we were talking about measuring from this wall to that back wall, right? So maybe the first one where E was from this corner to over there. But now where I've got E, maybe it's from right here to that wall. Does that make sense? Well, that distance, what you notice about that distance, no matter where I move E, it's the same. Okay, it does not change, right? It's constant. All right. If these two lines were going to converge, okay, this might take a minute for me to do. You guys know what converge means? Come together. They're gonna. It's another word for maybe intersect, right? So those two lines are going to intersect eventually, right? If I find a point on that line, and I want to go perpendicular from that point to there. So that, perpendicular from that point to that line. That is going to provide me the shortest distance from that top line to the bottom line. Okay? So that there is the shortest distance from E to that line right there, correct? But as I move okay, so it's 3.92. Okay, if I'm standing at point E and I want to walk to this line right there, okay, it's going to be 3.92 as a distance. Okay, but as I move E, what do you notice happens to that number of 3.92? It starts to change now, right? And because it's changing, it tells me mathematically that those two lines, the distance between them is getting smaller and smaller and smaller, and eventually that distance between them will become 0, and that's where they meet, right? Okay. So the idea with parallel lines is that distance does not become smaller. Okay. Therefore, those two lines will never meet, right? So another way, a phrase that you're going to hear me say, and you might hear in other courses, that defines parallelism is that it is when the distance between two lines is constant. Okay. Constant means doesn't change, right? Okay, so the distance between two lines is constant is another way of talking about parallelism. Okay, there's some stuff that is in this slide and in the previous slide that kind of reminds you of how you dealt with parallel lines last year algebraically with systems of equations. But for just the time's sake right now, we'll kind of skip that. But there is a direct link between everything you did last year and everything we do this year. There is a direct link. Okay, so we'll talk about some of that stuff later on. This definition, skew lines, is the same exact definition as what we just talked about for parallel lines, but we negate the definition. Okay, where it had coplanar, now we say it's non-coplanar. Okay. So you had coplanar, we now have non-coplanar. So skew lines are non-coplanar lines. Okay, that means they are not parallel because to be parallel said they had to be coplanar, right? So once I introduce the word non-coplanar, it eliminates being able to be parallel. Okay, and they do not intersect. Okay, so skew lines are non-coplanar lines that do not intersect. On your test in the chapter 3 quiz, one of the first vocabulary words will be these are two coplanar lines that do not intersect. And the next question will say these are two non-coplanar lines that do not intersect. Okay? And every year somebody comes back and says, you put the same question in here twice. And then I just don't read it. Read it again. Okay? Because it's really easy to kind of glaze over that negation, that non. Okay? So make sure that when you are reading questions, you're being deliberate and you're slowing things down to make sure you're reading it and interpreting it the way it's phrased. Okay? So skew lines and parallel lines, very similar definitions, but we have that difference between coplanar and non-coplanar. If you remember, we talked about this before. I'll bring up a picture here of skew lines, kind of mess around with. Computer's slow today. All right, so this is just a series of skew lines, but the idea is that they never intersect. Come on. There we go. All right, those two lines do not intersect, right? Okay, but hopefully you recognize they are not parallel either, right? Parallel meant they had to be coplanar. These are non-coplanar because you can see right now the plane that contains the blue line, right? The gray plane is a plane that contains the blue line. I'm going to need another point here, but maybe plane, select 3 points, or a point in a line. Okay, so let's do this. Let's say I put that point there. So I can select that point, and that point, and now I get another plane. So you see that the red one is in that bluish plane, right? And the blue one is in the gray plane. There is not a single piece of cardboard that we used as the planes before that would contain the entire red line and the entire blue line. Does that kind of make sense? Okay. You need two separate planes to contain the red line and the blue line, so that means they're non-coplanar lines. If they don't intersect, then we identify them as skew. Okay. A way I always kind of help myself remember, and this comes from like barbecuing or whatever. When you barbecue, like shish kebabs, what's the rod you put through them? Skewers. Okay. And the logic and why they're called skewers is you're taking whether it be the vegetable or the meat or whatever you are skewing. Okay. You are skewing the plane of that object. Okay. So here's my my steak here, which is a plane, right? I think about the surface of that steak. It's a plane. Well, if I draw any line in that plane, maybe I draw that line right there in the plane of that steak. Take a Sharpie and draw on my steak. Okay. Will my skewer ever intersect that line that I drew on my steak? No. Okay. Therefore, those two lines are always going to be the skewer as a line and the line I drew are going to be skewed to one another. That's why they're called skewers. Does that make sense? Okay. So that helps me remember the difference between parallel and skew. Okay. Parallel planes, same idea. Okay. Parallel planes are two planes in which the distance between them is always the same, or the parallel planes are two planes that do not intersect. Okay. A lot of times the way we like to think about it is like the ceiling and the floor are parallel planes, the wall in front of you and the wall behind you, they're parallel planes. Okay. In construction, for the most part, I'm going to guarantee you that the ceiling is not 100% parallel to the floor. Okay. If we were to extend the ceiling out for infinity and extend the floor out for infinity, they will intersect some point. Okay, it might be millions of light years that direction, but they're going to intersect somewhere. Okay, because the idea is if I were to take my tape measure and go straight from the ceiling straight to the floor, make sure I use a perpendicular line from the ceiling to the floor, and I measure that distance right here, and then I go every other point in the room. So there's an infinite number of points of doing that. Somewhere the distances are going to be different. Does that make sense? Just because of the human error that is created when we construct things. But theoretically, we want the ceiling and the floor to be parallel. Okay, we want this wall in front of us to be parallel to that wall behind us. Okay. What is nice is that we can do a couple small measurements with right angles to help kind of guarantee that the best we can inside construction. And I'll explain that kind of stuff when we get there in the next couple days. But parallel lines kind of view in the same way you do parallel planes. Parallel planes view in the same way you view parallel lines. And they are symmetric as well. Okay, if the ceiling is parallel to the floor, then the floor is parallel to the ceiling. So that's talking about parallel stuff. Okay, do you guys have any questions on that? Hopefully it wasn't new. That's kind of old information, right? But maybe alternative ways of thinking about it, alternative ways that you're going to hear me talk about. Okay. Now I want to talk about what we call transversals. Okay, and you've heard this before. You've seen this information before, but we need to talk about it, make sure we're all on the same page because of how we're going to use it tomorrow. Okay, transversal is just a word that we use to talk about some type of line, and that line has a feature of intersecting two other lines. Okay, and it really could be 3 other lines or 4 other lines or 5 other lines, however many other lines we want. Okay, but those lines have to be coplanar. So a transversal is going to intersect more coplanar lines. So 2, 3, 4 other coplanar lines. Okay, which is nice to talk about coplanar because it's going to create some very rigid relationships tomorrow that are really, really nice to have and understand. So in this case, lines L and line M, those are your 2 or more coplanar lines. Okay. Line T here is your transversal. Okay, so that's what that definition is getting at. And when it says distinct points, the reason it says different or distinct points is to eliminate the possibility of your 2 lines that you're dealing with being the same line. Okay, because we ultimately want this picture. No matter how we have lines intersecting, we want this picture. Okay. Now that picture might be rotated. The lines might be further apart. There might be more severe slopes with the transversal, whatever. But we're looking to try to gain that image somehow. And my computer is frozen, so give me a second. I think I got too many things open. All right. So when it says this thing, so we could have that image. We can have that image. It's really all the same. If I zoom in far enough, it's the same picture that I had in the PowerPoint, right? But this line can change all at once. It's still the transversal, okay? This line here can change all at once, and this one can change all that at once as well, okay? But the idea is that this transversal needs to intersect the blue lines at different points. And we see those two different points, G and H here. If we make G and H the same point, we don't get the relationships that we want, because now we just have two lines intersecting, right? And that kind of defaults it back to information that we already know. That basically creates vertical angles and supplementary angles, right? Relationships that we already knew, we've already talked about in previous lessons. So now we want to talk about what happens when we have two distinct lines in which the transversal intersects at two different points, okay? So we'll force always a picture like that. When we talk about transversals, there is always kind of a division of the plane and some areas that we need to talk about, some regions. Come on. All right, so the regions that are created here, stupid. All right, we've got the region between the two lines, okay, the yellow region, okay? Now that picture could be rotated, so it doesn't always have to be kind of like a horizontal region. The picture could look, can we rotate this? Come on. Well, I don't know what's going on with the period. Did this last period and just kind of stopped working eventually. But we've got that yellow region. We call that the interior of your two lines. Okay. If I can locate my interior, I can then also locate the exterior as being everything else. Does that make sense? Okay. So you got your interior region. You got your exterior region. The reason we want to be able to identify those is because angles 3, 4, 5, and 6. Because they're all interior angles, they're going to relate to one another nicely, okay? Because 1, 2, 8, and 7 are exterior angles, there's going to be some nice relationships that allow them to relate to one another, okay? There are already some relationships that you already know about these things. What do you know about angle 1 and angle 3? What types of angles would they be? Jim? They're vertical angles. What do you know about 1 and 2? Linear pairs. So we've got supplementary angles, and we got some congruent angles up there, right? So those are already relationships that we know. But eventually what we want to do is, are there going to be relationships between maybe angle 4 and 6? Is there going to be a relationship between angles 3 and 5 and so forth, okay? So we need to be able to talk about where the interior is and where the exterior is, all right? All right, so the next definition is what we call alternate interior angles. The definition of the word tells you exactly where to look. Okay? Alternate means to do what? To switch, to change, to go back and forth between, right? So those are all valid ways to think about alternate means. Interior means on the inside, right? So hopefully interior, we already know what that was from last slide. But alternate now references the transversal. Okay? So the word interior, or maybe the word exterior, references lines L and M. Okay? The word alternate references the transversal. Okay? So when I say alternate interior angles, they're going to be on different sides. They're going to switch back and forth from one side to the other of the transversal, and they're going to be on the inside of lines L and M. So when I look at angle 4 there, okay, if I just think about alternate interior angles as being on the inside in different sides of the transversal, 4 could ultimately be paired up with 3 or 6. Does that make sense? Okay. we want it to be paired up with just one of those angles, okay? And what happens is that we kind of, as authors of the textbook, we know what we're going to do in the next section with lines L and M, and we know that we want to talk about 4 compared to 6, okay? Because we already don't we already know a relationship between 4 and 3? Yeah, they're a linear pair, right? So that's a relationship that's always going to exist between those two angles. So it's not new stuff, okay? So we want to see if there's a relationship between 4 and 6. So what we do is we add this word right here, non-adjacent, to our definition. And that forces us to look at angle 4 compared to angle 6. Does that kind of make sense? All right. 3 and 5 are also a pair of alternate interior angles. Okay? So you're always kind of looking I kind of visualize it as diagonals of one another. 4 and 6 are kind of diagonal from one another. 5 and 3 are kind of diagonal from one another. Okay? So those are alternate interior angles. What do you think you would call angle 1 compared to angle 7? Good. Alternate exterior. Okay, so be a minute, but see if we can scroll through to that definition. Alternate exterior angles, okay? Same exact definition, but they keep the word interior out and they put the word exterior, okay? So my hope is once you learn one definition, you know the other ones, okay? Still have to be non-adjacent, because what's the relationship between 1 and 2? We already know that, right? They're supplementary, so it's kind of redundant to come up with a new relationship, okay? We don't get anything new from there. So we want to look at 1 and 7. So 1 and 7 are non-adjacent exterior angles, so we call them alternate exterior angles. Still kind of a diagonal relationship there, isn't it? Let's see if we can erase that stuff. So 1 and 7 are alternate exterior. 8 and 2 are also a pair of alternate exterior angles. Okay? And we're going to do a lot of work with those things in the next couple days. What if I asked you to look at 3 and 6? 3 and 6. Are they interior angles as well? Yeah. Okay, they're interior. But what side of the transversal, how would you phrase what side they're on compared to one another? Are they alternate anymore? Now, so what's the wording that you might use? Not adjacent, because they have to share a vertex to be adjacent. They don't share a vertex. What side, if somebody was, or what to one another in regards to the reversal? They're both on the same side. Okay? So 3 and 6 are referred to as same side interior angles. Same side interior angles. It looks like my computer has totally frozen. Okay? So we should be okay to get through the rest of them. But 3 and 6 are same side interior angles. And by definition, all we have to do for same side interior angles, they are angles that are interior. They're interior angles that lie on the same side of the transversal. We don't have to add that word non-adjacent in there, because 3 and 6 automatically, by their existence, are non-adjacent. Okay? Because they don't share a vertex. So same side interior angles are a pair of angles that are on the same side of the transversal on the interior of the two lines. In the next one, the last one, and then I'll set you free on your homework. I wish I could get to show up though. I think the problem with the computer is that I've got that video recording, and there's a couple other apps that are open in the background that's slowing things down. But same side interior, and now we have, I want to look at angle 2 compared to angle 6. Angle 2 compared to angle 6, or angle 3 compared to angle 7. Okay? So those types of angles are referred to as corresponding angles. Okay? And the word corresponding just simply means to match. All right? If I ask you, thinking about classrooms on the second floor and how they correspond to classrooms on the first floor. Okay? Mrs. Oliver's class, what would that correspond to on the first floor? Yeah, Mrs. Yu's class, right? Who would, Mr. Gomez's class is going to correspond to what? Mr. Seidel's class, okay? So when we're thinking about corresponding with transversals, is that I like to look at like this line L here as kind of the second floor, okay? I like to think about line M as the first floor, okay? And then these angles 1 and 2 being kind of classrooms on the first floor, or sorry, on the second floor, and 5 and 6 being classrooms on the second floor. Does that kind of make sense? Okay. All right, I messed the floor. Second floor, first floor, doesn't matter. But if I look at line L and say angle 2 is a classroom, what classroom does that correspond to on line M? 6, right? Okay. They are matching. Okay. Now they're not equal here. Angle 2 is not equal to angle 6, but they are matching positions, and that's what we mean by corresponding when we get into geometry. We mean matching positions. Okay. So 2 and 6 correspond. Would 3 and 7 correspond? Are they matching positions? Okay. 1 and 5 and 4 and 8 are also corresponding. Okay. A way I like to think about it is I always visualize if I'm dealing with corresponding angles, take line L, okay, and you can do this with M too, but allow it to be kind of free floating, and you can drag it down and move it, and as you drag it down and move, your angles 1, 2, 3, and 4 are going to come with you. And if I drag that down and lay it on top of M, does 2 end up morphing on top of 6? And the angles that land on top of each other end up being what we call corresponding. Okay? Is that something we can do? A lot of your homework tonight is just recognizing things that are parallel, things that are skew, looking at a picture, trying to analyze it and determine what is alternate interior, what's alternate exterior, that kind of stuff. But hopefully it should not take you a long time. But it is extremely important that you come to class tomorrow and you know the series of 8 to 10 vocabulary words that we talked about today. So I'm going to try to get that posted for you here. All right, that should be available.
Amen.